So today we're going to start out with Conrad. He's going to be talking to us about WebRTC and the last mile. He's kicking off day 2. Let's give him a warm round of applause. Conrad?
Thank you very much. And thank you to Bogdan and his team for hosting this event and giving me the opportunity to talk to you this morning. And the topic, as you heard, was WebRTC and the last mile, because the last mile for a WebRTC communication represents some unique challenges. For us, we're going to unpack that. But before I do, which is sort of tradition on these presentations, I just take you through a little history of myself. My name is Conrad de Wet, and with regards to VoIP, in any case, my history is that in 2010, I put together a asterisk-based cloud PBX system. We called it Euphoria, and last time I checked, it was something in the region of about 70,000 extensions running on it. But about 5 years ago, I stepped back from things operationally there and sort of with my spare time put together a GitHub project called the Browser Phone. And it was designed to be a fully featured SIP-based WebRTC phone for Asterisk and FreeSwitch. And there's a little GitHub link for you. That's where the repo is. It's still available, free and open source. But it gathered quite a lot of interest, and it's cloned many times a day. And so last year, a little over a year ago, I decided to sort of form an actual company to provide Browser Phone as a service with the objective of creating a soft phone based on WebRTC and delivered, to the web and as a mobile application. And where OpenSips comes in is, of course, it is the proxy registration for that system. So there's a website address. You can have a look a little bit more. At the moment, it is free to use. There's a commercial model coming out soon. So let's have a look at the problem WebRTC. Peer A wants to connect with peer B. As illustrated here, the two users on the internet will need a signaling server in between. So there's a bunch of equipment which we will cover, like the stun server and the turn server and the signal server, which would be something like OpenSips, which may be in your control, but you are not going to be able to control where user A or user B is and what network they're on. So this introduces a problem. OpenSips can see and will handle the messages, no problem, but the media will eventually flow, as illustrated in purple at the bottom there, from user A to user B. And this last mile will have variables which are going to be out of our control. We may have jitter, packet loss, and we'll have to handle NAT and all these kind of stuff. And of course, user behavior. If the user chooses to switch from Wi-Fi to LAN, we'd need to be able to handle this. And this may be outside of the typical tools that we have, and things like OpenSips and things like that may not be in the media path. So we have lost visibility of the media, and we still need to be able to troubleshoot this, and we're going to have a look at what are the tools that we have at our disposal and what we can do. So I've broken this presentation down into sort of 3 sections. First of all, looking at what OpenSips can do, specifically with regards to ping and the options ping. Then I'm looking at the client side, at the browser side. There is an API called the RTC peer connection. We get some information from the get stats. I'll take you through that. And then we have a little demonstration on what a network failure or in the demonstration is actually a network switchover initiated by the user, and how we handle that and the re-invite for that. So going to OpenSips, having a look at the configuration. Sorry, this is a bit dry and a bit boring, but essentially we deploy something called the NAT helper module in OpenSips, which I'm pretty sure a lot of people are familiar with. But if you're not, essentially we configure with the modparam option. Some of the interesting things we've got, for example, the NAT ping interval. I've set it here to 120 seconds, and I have also indicated what flags I'm going to use in order to signal that I must perform the options pings on these registrations. I've included another one here, this flag, calculate latency. I'll show you where I use it later. And we're going to start collecting that information. Another interesting one here is the thresholds and the max pings lost. For example, we can give it a maximum time that the options message actually takes in order to round trip. If it exceeds the 3 seconds, it'll consider it lost. And then the count for that being 5 is if you have 5 sequential packet losses, then it can delete the entry in the connections table, and then essentially that user is considered offline. So if we have a look at how we apply this in the routing logic, I've called it a register route, but essentially as part of the registration flow, you'll use the set B flag to indicate that you want to ping this user. Here you can see we're setting the B flag for the ping return, which would monitor when the option packets gets lost and that we can delete the user. And then of course for calculate latency as well, we will use the set B flag for calculating latency. And this is the event route that we use to capture the return. So when the option packet is sent down to the client from OpenSips, it is returned into this event route, E_UL_ latency update, and we collect the actual latency as a microsecond with this parameter over here. Now, this example is just me logging it out, but you will typically save it to storage for you to display, and I'll show you how we do that later. Now, about a year ago, I reached out to Bogdan, and I said that OpenSips was sending the options messages, but not directed at the client. So we use a SIP library called SIP.js, and SIP.js was rejecting the options messages because it wasn't directed at the client. So here we can see that this options message is directed at SIP:alice at the destination IP address, and SIP.js was expecting the options message to be sent to it specifically, and OpenSips wasn't doing that. But a quick patch, and thank you for that, because after that, the options package, options messages were being sent correctly, and I could time the reply, and I could build out some data based on that. So, is that presents for me? Okay. So it's movie time. What I'm going to show you here is what you could do when you collect that information every 120 seconds. When the options message gets sent out and returned, we capture the time that it took to do that, and we store it in a database, put it all together with the contact, so when this user goes to their dashboard, they can see something like this. So what you'll see is that it starts with a latency of around 217 milliseconds, which is not really very good. We've got things like averages, we've got a count, and then if you use something like chart.js, then you can plot it out according to the data that returns. So here we can see just every 120 seconds, we're putting down a data point indicating the timeouts as well, lost packets, all that kind of stuff. You can see the most took 600 milliseconds. All right, and build a nice idea to the customer of what their network looks like from an options ping perspective. These are the actual raw data points that we capture for contact insert, update, and delete as well. So we capture that. And here's the raw message that was captured each time the latency ping was replied to. So you can see we're taking a snapshot of the actual time in milliseconds and storing it to a database. All right. But remember, this is the path that is signaling between the client and the actual OpenSips instance, which just allows Alice and Bob to find each other on the internet. The latency that we see here, 200 milliseconds, is not necessarily the path that the media is going to go. All right. So now we're going to turn our attention to the RTC peer connection, but we need a little bit of background for this. Now, obviously, I don't need to explain to everybody here what network address translation is, but there's some key points here, and that is that in a WebRTC scenario, we're undoubtedly going to be dealing with NAT. Two users on the internet are pretty much assured to be behind some sort of NAT environment. There's, of course, an exception for purely a LAN-based solution, but we're not really going to worry about that here. The WebRTC signaling, when it is established through the WebSocket connection, will then not have the same problems as UDP and NAT, because it is, of course, a stateful TCP or TLS, actually, connection between the browser directly and the OpenSips service that's running it. So NAT is not really, doesn't really come into play from a signaling perspective, but WebRTC media is not following the path of the signaling. When user A reaches user B over the network, the media goes directly peer-to-peer. But in order to send media from one user to the other over the internet, user A needs to be able to advertise to user B what their live IP address is. How is this media going to get from user A to B? And for that, user A needs to actually know its own live IP address, right? Which for a web browser is a considerable feat. And it's done with something called interactive connectivity establishment. So this is a process that occurs as part of the invite. This is not got anything to do with registration. I know OpenSips would know my IP address because I registered with it, but this is a different process, remembering that my signaling is done with TCP and my media is UDP. So we're not really talking about the same thing. So when it comes time to invite Alice and Bob, the ICE process will form part of the initial invite. And it is a process that forms part of the SDP, not the typical SIP headers. So what happens is that when Alice wants to call Bob, a request to the stun server is sent, and that is your session traversal utilities for NAT. I know it's a mouthful of various different acronyms, but there you go. What happens is the stun server will reply with an ICE candidate. This ICE candidate contains the full network path that it took in order to reach the external server. So all this information is returned back to the peer connection object. It's inserted into the SDP and sent over to Bob, so that now Bob understands how it's going to send its media back to Alice. All right. So this ICE establishment, the ICE candidates are an important part of WebRTC technology. There is also something called a turn server, a traversal using relays around NAT, another mouthful, but essentially what the turn will do is it will advertise itself as the IP address that you can use to send the media through. In other words, it's a sort of a fallback. If you cannot reach, if Alice and Bob can't reach each other directly, the turn server may sit in between Alice and Bob and allow media to go through it. It does introduce another leg in the media path, so it's something which people are trying to reduce, but it can help in various situations. All right, so before we go onto the getStats function, we need to understand that in order for Alice and Bob to have a media stream, we need the ICE candidates, the ICE candidate IP address that was returned from the stun server is the IP address that we're sending our media to. And so when we use our function called getStats, we're actually querying the media statistics that were sent directly from Alice and Bob. And what we can do is we can get things like packet rate, jitter, round trip time, and even packet loss. So it's a simple method. I can show you some code in a second on how to retrieve that information. But before I do that, the peer connection API is pretty powerful, but it does sort of leave us with the question, but what can we actually control? What is in our control? We are busy sending media to Alice. Can we do anything about that media that we are sending? So it turns out that by using something called set parameters, which is a function of the RTP sender object, we can reach the encoder, which is my outgoing audio or video encoder. It will depend on what sender you're attached to. And I can set something called the max bitrate, right? Now, typically a codec in use like Opus codecs or something like that will adjust its bitrate accordingly to what it can send. But what happens if you're in a multi-way video conference and you're not in display? So there's no need to actually send your media at all. So max bitrate can be used if you can communicate between users to reduce your bitrate to a very low rate and allow other media to consume the rest of the bandwidth. The other thing you can do, if it was a video, you could, for example, set the height. You could set the height to something really small, allow other videos to flow better. So we can use some of these tools to reduce our own sender abilities. So we have the ability to adjust our own sending rate. We won't really have the ability to adjust what we receive. That is what is up to the other person. All right, so let's have a look at some of the script that we use to collect this data. Here's a sample snippet of a peer connection and a simple set interval. The set interval is set for 1 second, so every second it's going to loop through the report from the getStats function. And for this example, all I've really done is logged it out. But again, I would store this data, and I would store this data locally. I wouldn't try and submit this data off to a cloud service while you're actually in a call, because then you're just going to be fighting with your own data. So I'd store this locally. Here I can get the packets received, I can get the round trip time, I can get the packet loss and jitter, and all the really valuable information that we want out of a media flow. Okay, remembering that this media went directly from Alice to Bob. You won't have any equipment on the route. You cannot tell this from your own controllable information. So you need to store it and monitor it locally. Okay, so another movie, and essentially what you're going to see here is you're going to see that I establish a call. It's a sample call. It's just to music on hold, just so that I can generate some data. There is no audio in this. In fact, audio is represented by data. So again, I use chart.js to plot out every second data points that I get from my get stats. Okay, so start a call. It's simple music on hold. Once I'm in a call, I then can go onto an interface which shows me my get stats plotted on a chart.js. The green represents the send kilobits per second and packets per second. You can see I've got about 30 kilobits per second sending there, and 50 packets per second as well, also in send. And red is represented in the receive kilobits per second, receiving also about 50 kilobits per second and 50 packets per second. It's about 50 packets per second as well. I don't have any packet loss, a bit of jitter, not too much though, 0.01. But these are the kind of statistics that we can get in a kind of live poll, all right? Now, to show you that this is a sort of real representation, I'm going to put the call on hold. So now I've marked the call as on hold. In an on-hold situation, I'm still sending 50 packets per second, but my packets are empty, so you can see my bitrate come down dramatically. But of course, I won't receive anything, right? So of course, my receive packets per second and my receive kilobits per second is gone. I've restored the call, and it restores everything, send and receive, back to normal. Okay. So this gives you an incredible insight into the actual packets, jitter, packet loss, all that kind of stuff on the call locally within the web browser space. Okay, so I've got a few minutes left, and for that, I'm going to take you through a network failure or switchover. And I say failure because essentially when a user chooses to switch over from Wi-Fi to 3G or LAN or whatever it is he chooses, it's essentially the same as pulling the cable out, isn't it? So whether it's a failure or a switchover, we're essentially saying for an amount of time, the user is going to be offline. Now, Siperb, I'm using version 0.20 and above. We establish a WebSocket something like this. We create event listeners for the various events. The only problem is that the error event listener can take up to 30 seconds to realize that it's gone offline if I change my own network connection, all right? That's just how it works. So this add event listener for error is only monitoring for server errors. It's only monitoring for situations where the WebSocket is disconnected on the OpenSips side. If the person goes offline and online, the only thing that is really going to give us a good indication of that is something called the window event listener, and it's got an event called offline and online. So offline is also kind of useless, because if you've gone offline, you're not sending any messages, you're not doing anything. So in fact, we do nothing on offline, because there's nothing we can do. You lost connectivity, right? We can indicate to you visually that you have lost internet, but I can't send any more messages. So the only one we're actually looking for is online during a call. All right? If you get an online event while you're in a media session, now we need to jump in. All right? And what we do is we collect the call information that you're in, save it temporarily. We then wait until you come online again and restore your call, right? But the important thing to remember is that the WebSocket connection will take up to 30 seconds to realize that it has gone offline. So when we come back online again, we remove the WebSocket. Even though it thinks it's still online, there's nothing you can do about it. We remove the WebSocket. All right, establish a new WebSocket, register, and send the re-invite. And this is what that will look like. So again, I'm using a call to music on hold, just as an example. I'm showing you here that I'm online. I establish a call, and again, I'll use the graphs to illustrate the actual audio. I'm not recording the audio. So here's the graph, sending and receiving as before, except like you do if you were on a WhatsApp call and the sound wasn't great, you can switch to Wi-Fi or you can switch to 3G. And I'm going to do that by literally switching my Wi-Fi over to my phone, okay, during a call. I hit the switch to my iPhone. You can see I'm still sending packets, right? Remember, I can't change that behavior. But you can see that the received kilobits per second dropped for a second. When it was back online, the invite was sent. My new IP address, as per my new ICE candidates, were then sent in my new invite, and it restored the call. Here we can see I'm switching back to Wi-Fi again. Same process, even quicker this time. There you go, there's a bit of packet loss, just to show you that I am actually recording packet loss. The whole time the JIT has been okay, but that is in fact a restored call with a new invite with my new ICE candidates. All right, so that's the end of the video and the end of my presentation. There's more information about what we're doing at siperb.com. You can download the soft phone, you can use it in your browser if you like, but that's it. Thank you.